Hello, everyone. So before we get started, I just wanted to give all the speakers an opportunity to talk a little bit about their backgrounds. For the most part, you've probably seen a lot of discussion about metal printing in the industry and producers here of metal printing. And our topic today is about high performance polymer and PEKK 3D printing. And this is kind of a brand new field, if you will. And so it may be helpful for you guys to hear about everyone's background and why we're here talking about this from different ends. My background is right now I'm coming from more of a consulting background, and as a professor, I'm really interested and have invested a lot in the science and engineering of how PEKK 3D printing works, starting from like the earliest 3D printers that were first commercially produced in the like I would say like 2016 was like the first PEKK printer, and I've been playing around with those in my lab since then. And it sounds like the folks at Curativa have been playing around on their own as well. So I just wanted to, Eric, do you want to say a few words about your background and how you came to be here talking about the first PEKK printer, and then we can just go around and talk about everyone's background, whether it's business, science, or whatever.
Yes, thank you, Steve. It's a pleasure to be here today. I have been developing biomaterials and doing research and commercialization of medical devices for over 30 years. And that's been very rewarding for me as I see technologies advance. In the early days of bone grafting, learning about how structure drives biology, fast forwarding to today with some of the technologies and analytical capabilities that we have that we didn't have even just a few short years ago. Looking to get, at the end of the day, better outcomes for patients. So taking a team approach to this, it's the materials and the systems that we utilize today are really multifactorial. They're very challenging, but they're very rewarding in the results that we obtain. So I look forward to sharing a little bit about what Curativa has been able to accomplish and look forward to the conversation.
Sure. Marcus, do you want to share a little bit about like your personal background and how you got to be here today?
Yeah, so thanks a lot for having me. My background is really on the metal side. So I started my career in 3D printing at Johnson & Johnson, where we looked into 3D printing of medical devices in 17.4. So instrument and 3D printing was my first gig, so to say. And over the last 5-6 years, I'm focusing within 3D systems on the titanium metal side, and I'm now really excited to grow the pie of applications and tap into PEKK 3D printing and discover new ground here.
Sure. Sunil, you want to talk about your background?
Yeah, sure. Yeah, it's really nice to be here. It's by accident that I'm here today. It was supposed to be Matt Canfor, who's had personal issues, and I'm actually substituting for him. But anyhow, it's a great idea to be here with the team. My background is being in polymer science, and at Evonik, we looked at this medical technology for a while, and for PEKK especially, it's a great time. We have developed a lot of technology over the time, and today we have come to a point where the industry is moving towards the 3D printing, and we were the first ones to jump on this as an active filament maker in this industry. So I really look forward to sharing some of those thoughts with you guys today.
All right. So I guess the first question, we'll get responses from everybody, but I guess the first question, when people are coming from metal and now talking about polymer implants, high performance polymer implants, like those that are made out of PEKK, there are two big questions one has to do, or two big mountains one has to kind of figure out about whether the time has come for them to be overcome. One of them is technical risk, like will it work? And then the second one is regulatory risk. Will the FDA allow it into the market? So I'd like for us to spend a good part of today talking about both technical risk and I think regulatory risk is more where we'll end up spending more of our time talking about today. And for those of you in the audience, if you have questions about where the state of the art is in either of those areas, I really do hope you'll raise your hand and we'll get you a mic and we can kind of answer your questions about that. So when we talk about technical risk of 3D printing using fused filament fabrication, so most of you are familiar with powder 3D printing of metals, right? And for PEKK, that's not really feasible for issues related to just the molecular structure of PEKK, which is why everyone is going to be talking about extrusion-based fused filament fabrication of PEKK. But for PEKK is a very fussy material, and it is not straightforward to do this. So the first challenge, which people have said it can't be done, is you can't fuse filament fabrication of PEKK. And obviously everyone here has kind of proven them wrong, because technically it is absolutely possible. Just because it isn't easy, it doesn't mean it's not possible. And I'd like to kind of have everyone here just say a few words about kind of overcoming that technical risk little hill, if you will, or how your own experience at your own organization was with going from kind of like, can we do this, to, yeah, we can do this. And maybe Eric, you're the best person to lead off that discussion with kind of I know you have some slides here about that.
Sure. I appreciate that. Before I head into the slides, just a little historical perspective that I think is helpful. I can remember in the late 90s when Victrex was first bringing PEKK over to the market here in the United States and through Envibio. And even way back then, the challenge was, how do we make PEKK more bioactive? How do we make it more physiologically friendly? And the fundamental nature of PEKK is it's hydrophobic and it tends to lead to fibrous encapsulation. So literally 25, 30 years ago, we were looking at trying to improve the fundamental aspects of PEKK. The fortunate news is that with this technology, with 3D printing, with additives or even without additives, you can get to the point where now PEKK behaves differently. So my background was ceramic engineering, and PEKK is one of those materials that it's a path-dependent material, meaning the way you handle it, the way that you process it, its thermal history, all those things can lead to final properties that are different. So the degree of crystallinity, the shape and the size and structure. And there's been a lot of research. Steve has done a phenomenal job with his team at the university, looking at triply periodic mineral surfaces, which are different pore structures that are engineered to create strength and to have a biologic benefit. So when I came to Curativa I'm going to say a little bit about that, literally just 3 years ago. So Curativa is a small company that was founded in 2017 in Rocket City, Huntsville, Alabama, where there's a lot of technology. And our goal was to provide a full manufacturing capability and a full spine line of implants, instruments. So we do classic manufacturing is in our DNA. We have CNC machines. Next slide, please. We have a state-of-the-art facility, and so we've produced several OEM implants as well that are some of the most challenging implants to make, as well as you can kind of see here on the right of this, there's a clean room over here, which is where we built to house all of our 3D printers. Next slide, please. So in terms of building a printer, we realize that each and every printer is going to be different. Each and every printer, in terms of how it controls putting the material together, especially with the polymer, is going to yield the final end results and properties. So the acquisition of a company called Fossil Labs and the inventor Todd Reith, the guy's a mad scientist genius, he built the machine from scratch. He built the firmware, he wrote the programming, he had understanding of the spine space through working at Globus, and he understood that he wanted to build the machine to control the material and to have all the critical build parameters completely under our own control. So there's other machines out there that will print PEKK, There's a Camovis, and I think APM has one.
Yep.
They're all going to be a little bit different in a lot of different ways. The temperature of the nozzle, the environmental temperature, the build plate temperature. And these are things that with material science input and engineering from a machining standpoint, and then the computer control of this, and I'll get into more from an FDA standpoint why this really made a difference, we believe, in helping us to be the first cleared 3D printed PEKK interbody implant. Actually, I think any implant, it's the first clearance of any implant, certainly through fused filament fabrication. So next slide, please. And this is the last slide I have, and we can let it dwell here, and I think it'll trigger some conversation. So we got FDA clearance in February of this year. And this is the implant, the cervical implant you can see in the right lower bottom here. And the idea is that we have pore structure, not only in the superior and inferior end plates, but all the way down through the implant adjacent to the graft window in the center. The graft window is a requirement by FDA. I could foresee in the future, or certainly in Europe, where you don't have a graft window. But this pore structure lends itself to bone integration, full osseointegration. It does that through its structure. So if I were developing a bone graft, I would probably have an interconnected porosity that had a pore size distribution of 100 to 600 microns. It's well established in the industry and the literature as being promotive of osteoconduction. But the real trick is to make sure that this is strong enough, as Steve laid out in the beginning. You look at that and you might think, wow, that's a lattice, it's porous. Is that going to be able to bear the weight? Is it going to be able to take the shear forces? Is it going to be able to be inserted and pounded in with a hammer as a surgeon will do in an interbody space? And the answer to all those questions is yes. Otherwise, I wouldn't have this slide that said we are FDA cleared. A call out to, and it's fortuitous that Sunil's here from Evonik, because as the provider of the filament, the Vestakeep i4 3DF, it was really important that it was a team partnership working with them, not only getting through FDA, but meeting our specifications and then integrating it into our printer. So as we went through the process with the FDA, we were able to print the implant that we wanted by design. We were very happy, as some other partners, Empirical, who's here on the floor, as well as MICRA as a regulatory partnership. It was really a team effort. It took 18 months to get the clearance, and as most of you know, a typical 510K is 90 days, especially on a PEKK implant. It should happen very quickly. But FDA wanted to really understand the process and the impact on the final properties. We were very confident that we could meet all the ASDM standards, but during that process of sharing information with FDA and getting them comfortable with this process, we did a lot of tests that went above and beyond. Testing the implant without the metal markers in there, as an example. Testing on impaction tests, for example, where we would go 3, 4, 5 times the physiologic load, smacking this to try to get it to fail. And be honest, to our delight, we had to go to very extreme conditions to fail this implant, and FDA wants to see what that failure looks like. There is some experience with titanium, selective laser sintering, where you see some of those fused linkages are very tough to control. And so unfortunately, when there is a failure, it can be catastrophic. You end up with a lot of particulate all over the place. We did not see any of that here. The toughness and the strength of each of these linkages is quite robust. And so a couple more things I'll say, and then I'll hand it back over. The image in the right is to the biomaterials group. This is a nano coating that's on there. It's a hydroxyapatite, calcium deficient hydroxyapatite. ProMimic has cultivated this technology for over a decade. It helps drive the biologic interface. And in the middle here, you can see a histology section courtesy of Professor Walsh, and a model that's been published extensively. And the pink or the red that you see there is bone growing completely through that implant. And I can tell you there's literally no fibrous tissue in there, which is uncharacteristic for PEKK. So the strength values here, and I'll say one thing as a lead-in, the properties of PEKK are very dependent, as I said, on temperature, rate of extrusion, rate of deposition. Our ability to control with the filament that we got from Evonik going from the amorphous to the crystalline state is very key to making sure that the Z-layer bonding is you're taking your footprint and then you're making a third dimension out of that. That's very instrumental in getting the strength values and the toughness values that we got. I'll just give you a quick example. The compressive strength, which is a very apparent test, if you take any of the cleared PEKK implants out, put it in a compressive ASTM 2077 compression test, they will fail usually under 8,000 newtons. Some of them are 2,000, 3,000 newtons, and they will fail catastrophically, meaning likely because of the large graft windows, they will buckle completely. This implant went up to 25,000 newtons, hit the limit of the load cell, and we stopped the test. It deformed a few millimeters, but it didn't fail as what I would call catastrophic. That's even in a porous implant, that's the degree of toughness that you can get with strain-induced crystallinity of these strands that are holding that lattice together. So that was a long lead into that, but I think the 510K clearance here, my hope is that the standard FDA held us to, that anybody that comes behind us, that their machine will have to meet those same standards, because at the end of the day, it's better for all of us that the quality of these implants that are going into patients will have the confidence of the surgeon and won't have some of the failures that might occur as these technologies are in their early stages. So.
Yeah, so just to underline what Eric was saying was that you today, using today's technology, well, in you're not planning on selling 3D printers, are you?
No.
Yeah, so in the hands of their mad scientists, they can print spinal cages that can take 5,000 pounds, like a decent sized car parked on top of it, and that's more than strong enough for today's cervical disc application. So I'd say that at least in their hands, the technical challenges were definitely surmountable today for PEKK, but that doesn't bring the technology out to people that are in this room or to hospitals where they want to potentially 3D print their own implants. And that is the solution that Kumovis, now 3D Systems, has been working on, which is developing a process for that. Can you say a few words about Marcus, about kind of the technical challenges and the technical hurdles that you've come across in developing your R1 printer?
So I actually would love to talk a little bit more in regards to the FDA clearance and touch on
Sure.
what you said. So certainly technical hurdles are one thing, and you touched on some of those, which I can just highlight. Yeah, we're facing the same challenges. But what I see happening right now in the industry is we created a lot of excitement, and your example definitely created a lot of excitement in the industry. Now the challenge is, how can we take the momentum we created and convert it into a level of comfort in the industry? Meaning, how can we make sure that across platforms we can approve and submit new devices and get this level of comfort in front of the FDA, but also in front of our customers when we talk about new applications. So growing the pie of applications is really something we want to address now. And I think there are several ways to do so. Right now, what we are doing is we are using extrusion guidelines and refer to them on the FDM side. And I see this pathway. Really, a few years ago, the same happened on the metal side. There was we knew, it works on in an R&D room. How can we get it from the R&D room out there and create the level of confidence in the industry? And really the same thing is repeating itself. We are using guidelines, trying to match those up, and helping now creating those guidelines, getting new devices, like we have one reference out there, getting new references out there. And I think that's the pathway really to get this level of confidence out there in the industry and make this as big as it should be.
Thanks, Marcus. Now, none of this would be possible if there was nothing to print. And so really crucial to developing a complete ecosystem was one of having a major partner willing to commercialize, like fully commercialize and support medical grade PEKK filament. And we're all glad, for those of us who are doing a lot of work in PEKK printing, that there is such a producer. Evonik is an example of one of the leaders. Can you just tell us about what you have a great business going on in just producing stock shapes and producing granules. What caused you to kind of go through the whole process of commercializing filament?
Yeah, so this was, I think, most people don't realize Evonik has been in 3D printing world for maybe 25 plus years. So we have another product called Polyamide 12.
Can you speak up?
Yeah, Polyamide 12. This is PA12, which you normally see in a lot of industrial applications. It's a powder-based printing technology, binder jet technology, SLS. I think it's already well established. So Evonik already had a good understanding of the 3D printing world, but it was always through a printer manufacturer. We were always in the background. In medical industry, it was changing because a lot of surgeons would come to us and say, hey, I want to print this. And also professors like Steve, he is one of the big catalysts who's pushing into this area, who said, yeah, I would like to print more PEKK and we would like to have more applications. So I think those are the combination of things which happened over time. And we already made materials which are processed traditionally, like injection molding and extrusion. And at that point, we were looking into expanding into the 3D printing, as we already had a portfolio in 3D printing, as I told you. For PEKK, the powder was not so easy. I think powder would have been easier if we said, okay, we have a PA12 powder, we could go to PEKK powder, and yeah, we would have taken the same pathway. But because we could not do that easily, we said, okay, the filament is much easier. And it also needed to find a niche market, because this is not a traditional market. And medical market came out to be one of the first ones where it works out really well. So that's where we said, okay, we want to make the first filament. We do see the vision that it will take over in this point of care technologies. I think this is the word which a lot of people are using. We started seeing this 5 years ago, and we really put an effort to bring out this filament. And I'm glad that we have really good partners from printer manufacturers as well as user application-wise, whom we can support to bring this application. Yeah. So Curativa is a great example. They've worked so hard to bring this through FDA. This is a really great story.
Does the Evonik filament for PEKK, is that supported by an FDA master file yet?
Yeah, I think it's listed in the file also, but our I4 grade is already listed, and that's the same material which goes into the I4 3DF, which is the filament.
Are there any questions at this point, or should we just keep on going? Go ahead.
This question's for Eric. Can you describe what drove the requirement for the Class 8 clean room for your printers? Why the printers are in the Class 8 clean room instead of in like a non-clean space?
Yeah, so for Class 8, it's not required to have environmental monitoring, but it's basically temperature and humidity control, and then throughput of a particular cubic foot of air per minute. And so it's not as robust as, say, a Class 100 clean room where you're gowning up and you're having to do environmental monitoring, where you might do aseptic processing. But one of the real big questions, and for fused filament, it's a little less concerning than if you're taking a laser and you're melting particulate and creating dust and other things. FDA was very concerned about contaminant in between each layer. And that makes sense, since you're basically constructing the implant 100 microns at a time, or maybe even less than 100 microns. And so there's a big opportunity for a contaminant to get introduced. And we felt that we wanted to go that extra mile to make it a really clean environment. And so that's why we went to an ISO 8 clean room.
Kind of as a follow-up to that, right? There are some producers of medical printers, and Kumovis is one of them, that are intended to operate in the hospital, and one of them is like literally on an operating room floor. Can you kind of talk about this concern about cleanliness and clean room, like
Yeah,
clean room in a printer kind of concept?
we addressed it slightly different. Instead of running our printer in a clean room, our printer, or the inside of our printer, like the print chamber, is considered a clean room already. So we kind of addressed it differently, with the idea to maybe have then our printer being able to establish it in hospitals and have point of care applications in the hospital. Yeah.
Would you say that the PEKK is more conducive to a point of care situation than powdered metals? And if so, I mean, what are the main drivers that would determine that?
So I would say that where there's a will, there is always a way. And so if you look at like Hospital for Special Surgery has managed to stand up a metal printing facility in their hospital in Manhattan. Oh, I mean, but like they were literally in the moving mountains kind of Manhattan money and energy being expended to kind of make that happen. Not everyone is going to have that same kind of same kind of energy, and so handling powder in a hospital-based environment kind of limits your technologies that you're able to use. But polymers and certain polymer printers can be engineered to kind of facilitate that in a way that it's very hard to do with powder-based technologies. Anyway, that's my 2 cents answered. Obviously, why don't we hear about Marcus? This is probably a good area for you to talk about.
Yeah, I agree. It is a door opener to your point. I think, yeah, there are definitely applications possible, which makes it easier to set up a filament machine than in previous days a metal machine. I think so. But that doesn't limit us on the industrial side either. So I truly believe that the development of 3D printed PEKK within healthcare application will not be only focused on point of care, and will make its way through volume manufacturing and patient-specific solutions as well.
Yeah, point of care is like the niche of the niche.
Yeah.
And it's driving research because it's super interesting and it's niche of the niche. But in terms of like everyday making the donuts, kind of making implants, as you can see from having all those printers on the factory floor, this technology is also super conducive to lining up a whole bunch of printers on a factory floor and kind of commercializing it.
Just to add a comment to that about getting into point of care, I've heard several people discuss this. There's a group that's working with the VA to basically produce and print parts. A lot of prototyping is being done right now in hospitals, but the challenge with an actual implant is that you have to have a quality system in place like all those companies do. So for a hospital, despite all the things that they already do, for them to adopt those quality processes and procedures is quite onerous and costly. So it can be done, but I think that's one of the biggest barriers to doing so. I also would have you take a look at the dental industry. That's always oftentimes a precursor to what we see in orthopedics. And now the dental industry, not only do they do CNC machining of copings in the dental office, they're 3D printing implants in the dental office. So where there's a will, there's a way. And I think someday that certainly a fused filament type application would be very well suited for those types of locations.
Yeah, and once HSS has printing in-house, you better believe Mayo's going to want it, and you better believe Rush is going to want it, right? So, and then once it's established at the big universities, then that is going to kind of filter down to normal hospitals as well. But keep in mind that the technology is not just intended for one-at-a-time implants, but really being thought of for kind of mass commercialization. And there are certainly some challenges of making FFF work when you're printing thousands of implants, but it's a different type of challenge than when you're trying to make one. Like 3D printing is awesome and has the greatest strengths in trying to make one-of-a-kind implants, and that's why it's academically and clinically super interesting. But it's also for making commercially implants that you couldn't make any other way, like porous implants with the kind of controlled porosity that you see kind of here from Curativa. It's not really feasible to kind of make that with traditional subtractive technology. Go ahead.
So I have a question for the panel. So what do you think about the bioresorbable materials? How the 3D printing industry think about the bioresorbable materials besides PEKK? PEKK is non-resorbable, right? But for the tissue regeneration, maybe bioresorbable present a bright future. So what do you think about it, particularly for Evonik person? Thank you.
So Evonik also has a portfolio of bioresorbable materials. And they also offer filament for 3D printing and powder for 3D printing. So there's already a very similar pathway for 3D printing materials. So PEKK probably came a little bit later, I would say, in this, but we had a great story with the clearance. But the same thing can easily happen with the resorbable side.
It's less newsworthy because it's so easy. Like every hospital, every library, public library has a PLA printer.
Yeah.
Now, from printing PLA to PLA is not. That's like rolling out of bed. It's super easy. What PLA and other resorbable polymers are really well suited to is blending with drugs, using in tissue engineering and regenerative medicine, and they're being used that. The only, I guess, there's some of the bioresorbables are more fussy to print than others. I think PCL, polycaprolactone, is the most fussy of all because has the opposite problem that PEKK does because it has to be printed at such a low temperature. It's like hard to get it to come out the extruder. It's kind of like printing a gummy bear. It doesn't really want to flow. And so you kind of need to talk about chilling rather than heating while you're printing. But standard PLLA, PLDLA, PGA, you can, I mean, that's like a senior design project at Drexel. I won't say it's like super easy, but it's not super technically challenging either.
No, good point. Yeah, from a printing point of view, I think we are there. We can do it. We have applications where we are printing inserts into our spine cages, for instance. That is something, especially in Europe, people are excited about. Not so much in the US at this point, but from a technology point of view, we're absolutely there to do that. Yeah.
Like from a technical perspective, PEKK is like the Mount Everest of difficulty of trying to 3D print something. And I guess PLA is like the bunny slopes where you're trying to learn how to ski. It's really super easy to learn that. If you wanted to print a high temperature polymer that is less challenging than Everest, you start with PEKK. That is like a very friendly, easily crystallizable. My students smile when I ask them to print something out of PEKK. With PEKK, it requires a lot more effort, but the technical challenges, as we're sitting here today, have been overcome. But a lot of the materials that you see walking around here, Radel, you can 3D print. Ultem, you can 3D print. Yep, go ahead, Dave.
Polyethylene.
Yes.
Yes, you can. Polyolefins are
Polyethylene.
Yes, so polyethylene. Yeah, polyethylene is so they absolutely can be 3D printed. They sometimes have trouble sticking. Adhesion, bed adhesion makes it a little bit fussy, and certainly as you go higher up and higher molecular weight, you can't really, like with ultra high, everyone's saying, why can't you 3D print ultra high? Well, it has no melt viscosity. You melt it and it's still like a solid puck on your desk. So the extruders don't have the heft to be able to melt extrude ultra high.
Quick,
fortunately.
Add a comment to the polyethylene that I think is parallel to what we've accomplished here. There is a company, a startup, Ben Holmes, the CEO of Nanocon, and they 3D print polyethylene, and they have a structure that drives the biology of hyaline cartilage, and they're using it for knee repair. So you look at osteochondral defects, that is very much a holy grail for biomaterials. It's very tough. You typically get fibrous and scar tissue, but to get type 2 hyaline cartilage is quite significant. So similar to this, they printed the right structure that the cartilage cells like to proliferate in. And so I think that we're going to see more of that. That's an exciting thing for me as a scientist, and seeing how biomaterials are improving. There was a talk yesterday about metamaterials generating electricity and generating currents that help repair tissue. And so as the knowledge of tissue engineering is advancing, the ability of old school traditional implants and technologies and systems to catch up with that, to cultivate that within the human body, I think you're going to see a lot more of that in the future.
Yes, you were talking about trying to print the various materials and talking about the extruders and whatnot. I'm curious about whether or not these materials can be printed in like an SLS process with powders, or do they have to be extruded?
Oh no, some polymers are well suited for SLS, and some are also well suited for fused filament fabrication. It's just a question of how much capital you have to buy a machine, right? I mean, if you want a powder printer, that's $1 million for a printer and $1 million or more for a facility to handle explosive metal powder. Oh, potentially, they say, explosive powder. But your health and safety folks will not consider it potentially explosive. They'll make sure that you do all of your remediation and everything else like that. I know because I've tried to have my lab upgraded to use a metal printer, and just to upgrade one room was like $500,000 at the university. So I was like, well, I guess I'm not getting into metal printing, powder printing. But in theory, if you have the capital and you want to build the facility, there are many polymers that are also well suited for SLS as well as FFF, like PEKK, for example, is well suited for selective laser sintering or powder-based processing, as well as extrusion. I mean, PEKK is kind of the Mount Everest. It was not ever, this polymer was never designed to be used in powder bed extrusion, was not intended to be used in FFF. It was intended to be used in injection molding, right? So the fact that the technological challenges have been overcome with this particular material is remarkable, but does not expand. It does not extend to like the universe of all other polymers that are out there.
And maybe to add on that, the FDM process comes with a couple of really neat advantages actually, which makes the whole process super exciting. So what we can do is, we are talking about carbon fiber reinforced PEKK, where you can actually align your fiber to the needs of your application, which is really amazing. Or we are talking about BCP filled PEKK, or we have Radel, to your question earlier, we have Radel with barium sulfide in it. So these filled materials, I see those growing quite a bit in the industry, and there is a lot of excitement around it, and obviously facilitated with the FDM process right now.
And as anyone who's ever played with an FDM machine in their basement, right, you get that instant gratification of being able to, I mean, I'm lucky to have a Kumovis printer in my lab, but so like when we want to print an implant, we can just press print. Like they design it with the software and it comes off the printer in an hour. And you don't necessarily have that same kind of flexibility with a super big extrusion powder-based system.
To add to that, one of the things, and for those interested in like how do additional machines get through the FDA process, having control of every step of the extrusion, every 3 seconds of what the temperature is at multiple locations, that's very critical. And when you think about controlling the multiple heat cycles that the material goes through, that was very important. And again, that's where the partnership with Evonik, doing a lot of the exhaustive testing that they wanted to see to make sure that the PEKK material wasn't denaturing or degrading in those multiple heat cycles. I think the ability to control that and to have actually a documentation of that, so the programming capability to say, almost like, you know, the old chart recorders, you know, here's a file that has every 3 seconds of all these absolute critical build parameters that is now documented. And so we know if something goes wrong during the print process. We know if the amount of extrusion has changed. We know if there's a fluctuation in temperature. We can look at the final part and know from its weight, its density, and actually the tightness of those parameters that from the first part to the 1,000th part that it's consistently being constructed. So that's a very important part of, I think, any FDA engagement is making sure you can document that.
Yeah, just
Yeah,
to add
that's-
to that,
Go ahead.
also just to add to that, like I think what Eric is saying about their controls, we also looked at the material aspect of it to make sure that nothing is coming off. I think the chemical analysis, which was required by the FDA, and talking to them, and their feedback was really important because this structure, as you see, is porous. And our first attempt was just taking the weight of the implant and then doing the analysis. And they actually came back and told us, like, this is highly porous, let's consider the surface area. And then we went back and did the analysis again. And this is, I think this is a partnership where they really helped us also understand what are they looking for. And we were able to provide that as well.
Any other questions? I mean, I think hopefully what you've had the opportunity to see is that there is kind of this whole ecosystem that has been developed for kind of traditional PEEK implants. It kind of lays the foundation for other technologies like making bioactive implants out of PEEK, and that this is just going to kind of continue to develop in terms of awareness of both regulatory and repeatability, kind of like research on like how repeatable is it from machine to machine and within this ecosystem. But we're really coming down to kind of the final stages of being able to nail down all the remaining challenges for this to go prime time. And then in terms of market acceptance, that's just a kind of wait and see for how long the technology proliferation takes. We are at time now, so I really want to thank you on behalf, and of course thank our hosts for inviting us here to have a friendly chat with you about this new and exciting technology, and thank all the speakers who came here to speak with you all as well. Thank you.
Hey, thank you very much.